Imagine standing at the edge of human knowledge, where every answer creates even deeper questions. For centuries, we believed that reality was something solid, predictable, and complete. We assumed the universe followed a script we could eventually read from beginning to end. But what if that confidence was only an illusion? What if, hidden beneath everything we see, there exists another layer of existence waiting to be uncovered? Today, we explore one of the most fascinating possibilities in modern science: the idea that CERN's experiments may have revealed clues pointing toward a reality far stranger than anything we have ever imagined. The greatest discoveries in history have rarely begun with certainty. They have begun with doubt, with curiosity, and with the willingness to admit that the world might be stranger than it appears. Every civilization has believed at some point that it had reached the limits of understanding. Ancient astronomers believed the heavens revolved around Earth. Early physicists imagined space and time as fixed and absolute. Yet each generation eventually encountered evidence that shattered its most comfortable assumptions. The frontier of knowledge has never been a destination. It has always been a moving horizon, retreating every time humanity takes another step forward. Today, that horizon exists in an extraordinary place, deep beneath the surface of Earth, where scientists are probing nature at scales so small that ordinary intuition loses its grip. When we observe the world around us, everything appears stable and predictable. Mountains seem permanent, stars seem distant, and matter feels solid. But this familiar picture is only an approximation shaped by our senses. Beneath everyday experience lies a universe governed by particles so tiny and interactions so subtle that reality itself begins to look unfamiliar. The closer we examine nature, the more we discover that certainty dissolves into probability, and simple objects reveal astonishing complexity. What appears to be empty space is anything but empty. Even the vacuum is alive with fluctuating quantum fields, where particles can briefly emerge and disappear according to the strange rules of quantum mechanics. This realization forces us to confront an uncomfortable possibility. Perhaps what we perceive is only a small fragment of reality rather than its complete picture. Human senses evolved to help us survive, not to reveal the deepest structure of existence. We cannot naturally detect radio waves, X-rays, neutrinos, or gravitational waves, yet all of them pass through us constantly. Technology has repeatedly expanded our perception, allowing us to uncover hidden aspects of the universe that once seemed unimaginable. Every new instrument has revealed that nature contains layers invisible to ordinary experience. Modern physics follows this tradition by building machines capable of exploring distances far smaller than atoms. At these extraordinary scales, scientists investigate the fundamental ingredients from which everything is constructed. They seek answers to questions that have challenged generations of thinkers. Why do particles possess the masses they do? Why are the fundamental forces so different from one another? Why does gravity remain so difficult to unite with quantum theory? Why does the universe contain vastly more matter than antimatter? These are not isolated puzzles. Together they suggest that our current understanding, however successful, may represent only part of a much larger framework. Standing at the edge of knowledge requires intellectual humility. Every successful theory in science has eventually revealed its own limitations. Newton's laws transformed physics, but later gave way to Einstein's deeper understanding of space and time. Classical physics explained countless phenomena before quantum mechanics exposed an entirely different microscopic world. None of these breakthroughs erased earlier knowledge. Instead, they expanded it, revealing that previous ideas were accurate within certain boundaries, but incomplete beyond them. This pattern encourages an important perspective. Scientific progress is not the replacement of truth with falsehood, but the refinement of increasingly powerful descriptions of reality. Each discovery uncovers deeper questions that were previously invisible. The more precisely we measure nature, the more clearly we recognize the gaps in our understanding. Every answer illuminates mysteries that could not even be imagined before the answer existed. That is why the search at the frontiers of physics is so compelling. researchers are not merely collecting data or confirming equations. They are testing whether the universe still holds fundamental surprises waiting beyond the reach of current theories. They are exploring whether reality possesses hidden dimensions, undiscovered particles, unknown forces, or entirely new principles that could transform our picture of existence. Every experiment represents a conversation with nature, asking whether the universe is willing to reveal another layer of its remarkable architecture. To understand why scientists build enormous particle accelerators, we must first imagine traveling backward through time, not by billions of years in a spacecraft, but by recreating the physical conditions that existed when the universe itself was unimaginably young. According to modern cosmology, the universe began in an extremely hot, dense state. During its earliest moments, temperatures were so immense that the particles making up matter behaved in ways completely unlike anything we observe today. As the universe expanded, it cooled, allowing energy to transform into the particles and atoms that eventually formed stars, galaxies, planets, and every living creature. Those first fractions of a second determine the structure of everything that exists, yet they remain beyond direct observation. Since no telescope can look back to the exact beginning, scientists have developed another strategy. Instead of observing the birth of the universe from afar, they recreate tiny pieces of its earliest environment inside laboratories. This is the remarkable purpose of powerful particle accelerators. By accelerating particles to velocities approaching the speed of light and smashing them together with extraordinary energy, researchers briefly generate conditions similar to those that existed just after the universe emerged. For an instant far shorter than a blink, matter returns to a state resembling its ancient origins, allowing scientists to study processes that shaped cosmic history. These collisions are often misunderstood as explosions. In reality, they are carefully controlled experiments designed to reveal nature's most fundamental ingredients. When particles collide at extremely high energies, they do not simply break apart. Their energy can transform into entirely new particles according to the relationship between mass and energy. Some of these particles exist naturally only under extreme conditions and vanish almost immediately. Although they disappear in incredibly short times, sophisticated detectors record the traces they leave behind, enabling researchers to reconstruct what occurred during the collision with astonishing precision. Surrounding the collision points are enormous detector systems filled with millions of electronic sensors. Every second, these instruments collect vast quantities of information, recording the paths, energies, and identities of particles flying outward from each collision. The amount of data produced is staggering, requiring advanced computing systems and international collaborations to analyze even a fraction of what is observed. Scientists search through these enormous data sets for patterns that differ from theoretical predictions, because even the smallest deviation could signal new physics waiting to be understood. One of the greatest achievements of this approach was confirming the existence of the Higgs boson, a particle whose discovery completed an essential part of the standard model of particle physics. Yet rather than marking the end of exploration, this success highlighted how much remains unknown. The standard model explains countless experimental results with extraordinary accuracy, but it leaves profound mysteries unresolved. It does not explain dark matter, which appears to dominate the mass of galaxies. It cannot fully incorporate gravity into quantum theory. It does not reveal why the constants of nature possess the values they do, or why the universe exhibits such remarkable order. Every new collision offers another opportunity to uncover something unexpected. Scientists hope to observe particles never seen before, evidence of hidden dimensions, or entirely new interactions that extend beyond existing theories. Even when experiments confirm current predictions, they strengthen our understanding by eliminating possibilities and narrowing the search for deeper explanations. Negative results are not failures in science. They provide valuable guidance by revealing which ideas nature does not support. What makes these experiments extraordinary is that they connect the smallest scales imaginable with the largest structures in the cosmos. By studying particles far smaller than atoms, researchers gain insight into the evolution of galaxies, the behavior of black holes, and the origins of the universe itself. Every collision becomes a tiny window into cosmic history, allowing humanity to investigate questions that once belonged entirely to philosophy and imagination, transforming abstract speculation into measurable scientific inquiry, guided by evidence, precision, and an unrelenting desire to understand the hidden foundations of existence. One of the most astonishing discoveries in modern science is that reality behaves very differently depending on how closely we examine it. In everyday life, objects appear to follow clear and predictable rules. A ball rolls across the ground, a glass falls from a table, and the planets move through space according to laws that can be calculated with remarkable precision. These experiences shape our intuition about how the universe should work. Yet when scientists explore the microscopic world of atoms and subatomic particles, those familiar rules begin to dissolve, revealing a realm so strange that it challenges the very meaning of certainty. At the quantum level, particles do not behave like tiny versions of everyday objects. Instead of occupying one precise position at every moment, they are described by probabilities. Before a measurement is made, quantum theory does not always assign a particle a single definite location or path. Rather, it provides a range of possible outcomes, each with its own likelihood. This is not simply a limitation of our instruments or our knowledge. According to the mathematical framework of quantum mechanics, uncertainty is woven into the fabric of nature itself. The universe, at its deepest level, appears to operate according to principles that are fundamentally different from common sense. Perhaps even more surprising is the phenomenon known as quantum superposition. Under certain conditions, quantum systems can exist in multiple possible states simultaneously until an interaction or measurement occurs. While this idea sounds impossible from the perspective of everyday experience, countless experiments have confirmed its predictions with extraordinary accuracy. The technologies that define modern civilization, including lasers, semiconductors, and advanced medical imaging, all rely on the principles of quantum mechanics. The strange behavior of the microscopic world is not philosophical speculation but measurable reality. Another remarkable feature of quantum physics is entanglement, a phenomenon in which particles become connected in ways that cannot be explained by ordinary ideas about distance. When two particles are entangled, measuring one instantly determines certain properties of the other, even if they are separated by enormous distances. This does not allow information to travel faster than light, but it reveals that nature possesses forms of correlation unlike anything found in classical physics. What appears to be separate may, at a deeper level, be part of a single interconnected quantum system. These discoveries force us to reconsider some of our oldest assumptions about reality. We naturally think of the universe as consisting of independent objects moving through empty space. Quantum theory suggests a far more subtle picture, where fields, probabilities, and relationships may be more fundamental than the solid objects we experience in daily life. Matter itself emerges from underlying quantum fields that extend throughout the universe, with particles appearing as localized excitations of those fields rather than isolated building blocks. As researchers continue exploring high-energy particle collisions, they hope to determine whether quantum mechanics remains complete or whether it represents only one chapter of an even deeper theory. Certain puzzles remain unresolved, including the relationship between quantum physics and gravity, the nature of dark matter, and the possibility that hidden dimensions, or undiscovered particles, influence quantum behavior in ways we have not yet detected. Every experiment pushes these questions closer to empirical investigation rather than philosophical debate. The strange behavior of quantum reality reminds us that human intuition evolved to navigate forests, oceans, and open skies, not the invisible world of subatomic particles. Our instincts reflect the scale of everyday experience rather than the architecture of the cosmos. Science expands our perception beyond those biological limits, revealing a universe whose deepest workings are richer, more subtle, and more astonishing than imagination alone could have predicted, inviting us to question whether reality is defined not by what seems obvious, but by what nature consistently reveals through careful observation, mathematical precision, and experimental evidence that continues to challenge every comfortable assumption we once believed to be unquestionable. For most of human history, the universe appeared to have 3 dimensions of space and 1 dimension of time. Length, width, height, and the steady flow of time seemed sufficient to describe every experience. From walking across a room to observing distant galaxies, everything appeared to fit neatly within this familiar framework. Yet modern theoretical physics has introduced a remarkable possibility. What if these 4 dimensions are only part of a much larger reality? What if additional dimensions exist all around us, hidden not because they are imaginary, but because they remain beyond the limits of ordinary perception? The idea of extra dimensions is not science fiction invented to make the universe seem more mysterious. It emerges naturally from several advanced mathematical theories that attempt to unite the fundamental forces of nature into a single consistent framework. These theories suggest that the universe may possess dimensions beyond those we directly experience. Unlike the dimensions we move through every day, these hidden dimensions could be incredibly small, tightly curled upon themselves, making them effectively invisible at ordinary scales. Just as a distant cable appears to be a one-dimensional line until viewed up close, space itself may contain intricate structures that remain unnoticed because of their tiny size. Some models propose an even more dramatic possibility. Instead of being curled into microscopic scales, additional dimensions might extend far beyond our perception, while ordinary matter remains confined to a 3-dimensional region, often described as a cosmic membrane. In this picture, gravity may be unique among the fundamental forces because it can spread into these higher dimensions. Such a framework could explain why gravity is so much weaker than the electromagnetic force or the nuclear forces. Rather than being inherently weak, gravity might simply be diluted across dimensions that remain inaccessible to our everyday experience. If hidden dimensions truly exist, powerful particle collisions could provide indirect evidence of their presence. When particles collide at extremely high energies, some of the energy might disappear from our observable universe by passing into these unseen dimensions. Scientists would not watch particles travel into another reality directly, but they might detect missing energy or unusual particle behavior that current theories cannot explain. Such observations would represent some of the strongest evidence that space itself possesses a deeper architecture than previously imagined. The possibility of extra dimensions also changes the way we think about the universe as a whole. Instead of imagining reality as an isolated cosmic stage, we begin to consider the idea that our observable universe may be only one region within a far larger multidimensional structure. This perspective raises profound questions. Could other regions exist with different physical conditions? Could the laws of nature vary across a higher dimensional cosmos? Are the constants that define our universe the result of deeper geometric principles hidden within dimensions we cannot directly perceive? These questions remain speculative, and science approaches them with caution. Extraordinary ideas require extraordinary evidence. Mathematical elegance alone is never enough to establish truth. Every theoretical proposal must ultimately face experimental testing. This is why particle accelerators play such a vital role. They provide opportunities to search for measurable consequences of ideas that would otherwise remain purely mathematical. Even the absence of evidence helps refine theories by eliminating possibilities that nature does not support. The search for hidden dimensions represents more than an effort to expand geometry. It reflects humanity's continuing desire to understand whether reality extends beyond the boundaries of ordinary experience. Every generation has discovered that the universe contains structures invisible to the naked eye, from microscopic cells to distant galaxies and invisible forms of radiation. The possibility of additional dimensions continues this tradition, reminding us that the limits of perception are not necessarily the limits of existence, and that the deepest structure of reality may still contain layers waiting patiently for discovery through observation, experimentation, and the relentless pursuit of knowledge that refuses to accept familiar appearances as the final description of the universe. Every major scientific revolution has begun with a moment when nature refused to behave exactly as expected. A tiny inconsistency in an experiment, an unexpected pattern in the data, or a measurement that could not be explained by existing theories has often become the first clue that a deeper truth was waiting to be uncovered. These moments are not dramatic flashes of certainty, but quiet invitations to rethink everything we thought we understood. Today, one of the greatest goals of modern physics is to search for these subtle signs that point beyond the standard model, the remarkably successful theory describing the fundamental particles and forces that shape the observable universe. The standard model has earned its reputation through decades of experimental success. It accurately predicts the behavior of quarks, electrons, neutrinos, photons, and many other particles with extraordinary precision. Its equations have survived countless experimental tests, making it one of the most successful scientific theories ever created. Yet despite its achievements, physicists recognize that it is incomplete. It describes only a fraction of what the universe appears to contain. Observations of galaxies, galaxy clusters, and the large-scale structure of the cosmos reveal the gravitational influence of dark matter, a mysterious substance that does not emit or absorb light and cannot be explained by any known particle within the standard model. Gravity itself presents another profound challenge. While quantum mechanics successfully describes 3 of the 4 known fundamental forces, gravity continues to resist complete integration into the quantum framework. Einstein's theory of general relativity explains gravity on cosmic scales with extraordinary accuracy, while quantum mechanics governs the microscopic world with equal success. Yet the mathematical languages of these 2 theories remain difficult to reconcile. This disconnect suggests that an even deeper description of reality may exist, one capable of unifying both perspectives into a single coherent framework. Particle accelerators provide one of the few opportunities to search directly for evidence of this deeper physics. During high-energy collisions, scientists carefully examine every particle produced, every trajectory recorded, and every unit of energy measured. If the standard model is incomplete, the collisions may reveal particles that have never been observed before, or interactions that cannot be explained by current equations. Even the smallest deviation from theoretical predictions could indicate the presence of entirely new physical principles operating beneath the familiar surface of reality. Researchers also search for evidence of hypothetical particles that could explain some of the universe's greatest mysteries. Certain theoretical models predict new families of particles that might account for dark matter, or reveal hidden symmetries within nature. Others suggest entirely new forces that become noticeable only at extremely high energies. Although none of these possibilities has yet been confirmed, each experiment narrows the range of possibilities, allowing scientists to refine their understanding with increasing precision. What makes this search remarkable is its commitment to evidence rather than expectation. Scientists do not begin by deciding what reality must be. Instead, they construct theories that make measurable predictions and then allow experiments to determine whether those predictions survive contact with nature. Many beautiful ideas have failed this test, while unexpected discoveries have repeatedly transformed the direction of physics. The willingness to let observation guide belief remains one of science's greatest strengths. Every collision inside a particle accelerator represents more than a technical achievement. It is a question posed directly to the universe. Does reality contain ingredients we have not yet discovered? Are there hidden particles silently shaping the evolution of galaxies? Do unknown forces influence the behavior of matter in ways that remain invisible at ordinary energies? Each experiment brings humanity closer to answering these questions, not by relying on speculation or imagination alone, but through careful measurement, relentless analysis, and an unwavering commitment to following the evidence wherever it leads, even if that path transforms our deepest understanding of the universe and reveals that the foundations of reality are far richer than the theories that currently describe them. Suppose humanity eventually discovers convincing evidence that reality extends far beyond everything we currently understand. Imagine that experiments reveal hidden dimensions, entirely new particles, or physical laws that reshape our picture of the cosmos. Such a discovery would not simply add another chapter to science textbooks. It would transform the way we think about existence itself. Throughout history, every major scientific breakthrough has changed humanity's place in the universe. We once believed Earth stood at the center of creation, only to learn that it is one planet orbiting an ordinary star in one galaxy among hundreds of billions. We once imagined space and time as fixed and independent, only to discover that they form a dynamic fabric shaped by matter and energy. Every expansion of knowledge has required an expansion of perspective. A deeper understanding of reality would continue this remarkable tradition. If hidden structures exist beneath the observable universe, then many questions that currently appear disconnected might suddenly become parts of a larger and more elegant picture. Mysteries surrounding dark matter, dark energy, gravity, and the earliest moments of cosmic history could become understandable within a broader theoretical framework. Concepts that today seem unrelated might eventually be recognized as different expressions of the same underlying principles, just as electricity and magnetism were once considered separate phenomena before they were revealed to be aspects of a single force. Such discoveries would also reshape philosophy. For thousands of years, thinkers have asked whether reality extends beyond human perception. Science has gradually replaced speculation with observation, transforming philosophical questions into experimental investigations. If future experiments reveal layers of existence previously hidden from view, humanity will once again be reminded that perception is not the same as reality. Our senses provide only a limited window into nature, while scientific instruments continue expanding that window into regions once thought forever inaccessible. The technological consequences could be equally profound, even if impossible to predict. History repeatedly demonstrates that fundamental discoveries often produce practical applications long after they are made. When quantum mechanics first emerged, few imagined that it would eventually lead to computers, lasers, magnetic resonance imaging, and global communication technologies. Likewise, understanding deeper aspects of reality may one day inspire innovations beyond current imagination. Scientific revolutions rarely announce the technologies they will create. Instead, they establish entirely new ways of understanding nature, from which unexpected inventions naturally emerge. Yet perhaps the greatest transformation would occur within human thought itself. A civilization that understands more about the universe also understands more about its own origins. Every atom within the human body was forged through cosmic processes stretching back billions of years. The elements composing our cells were created inside ancient stars before becoming part of planets and eventually living organisms. Learning more about the universe is therefore not separate from learning more about ourselves. We are participants in the same cosmic story we seek to understand. The search for deeper reality also teaches an enduring lesson about knowledge. Every answer reached through careful observation has revealed further questions waiting beyond it. Scientific progress has never been a journey toward final certainty, but an ongoing process of refining our understanding. Each generation inherits mysteries from the previous one while uncovering new mysteries for those who follow. This endless pursuit is not a sign of failure, but evidence that reality possesses extraordinary depth and richness. Whether future experiments confirm hidden dimensions, reveal unknown particles, or strengthen the theories already in place, the true achievement lies in humanity's determination to keep asking questions that once seemed impossible to answer. The willingness to challenge assumptions, test bold ideas, and accept whatever nature ultimately reveals defines the scientific spirit, reminding us that the universe is not obligated to match our expectations, but it continually rewards curiosity with deeper insight into the remarkable reality we inhabit, encouraging every new generation to look beyond the horizon of accepted knowledge in search of truths that remain patiently hidden within the vast architecture of the cosmos.